Good afternoon, friends, and welcome to another class of Parijat Sir classes. And today I would be discussing with you another chapter of optics, which, as you can see, it is the diffraction and polarization of light. Diffraction and the polarization of the light. So, class 12 physics. It is continuing the physics classes, and today's topic will be the topic from optics, which is diffraction and polarization of light. This is my personal number. You can contact for any personal guidance if you require. Please keep watching Parijat Sir classes and like, share and subscribe my channel so that you can get a complete view of the all the classes which I will be uploading to you, and this is the complete notes of each and every chapter along with the numericals I will be discussing with you. Okay, so without wasting any time, let's continue with the chapter diffraction and polarization of light. First of all, what is diffraction of light? What is diffraction of light? Okay, so let's see the diffraction of light. So it is, as you can see, it is the phenomena of bending of light around corners of an obstacle or an aperture in the path of light. So as you can see, if light is moving like this, as you can see here, if light is moving like this, whenever it faces the aperture, this is the aperture, this is the aperture. Okay, so the light will start to bend. The light will start to bend from the aperture. So more the aperture is smaller, the light will bend more. The light will be bending more and more, and this will take the form of a spherical front. This will take the form of a spherical front. And if the aperture is bigger, the light will take the form of plane wave fronts. Okay, so this is the thing. Whenever light passes through an aperture, it will bend around the corners of the aperture. If the aperture size is more, it will take the shape of a plane wavefront, and if the aperture size is comparable to the wavelength of the light, if the aperture size is comparable to the wavelength of the light, the waves coming out will be of the spherical shape. Clear? Now, on account of this bending, light penetrates into the geometrical shadow of the obstacle. So light is penetrating like this. Thus light deviates from its linear path. That means from this corner of the aperture, the light will start to deviate out. The light will start to deviate out. Okay. The diffraction is most if the slit width is comparable to the wavelength of light. That means if the slit width is comparable to the wavelength of the light used, the diffraction will be the maximum here. See, thus narrower the slit, greater is the spreading. According to Fresnel, diffraction occurs on account of mutual interference of secondary wavelets starting from the portions of the wavefront which are not blocked by the obstacle, or portions of the wavelength which are allowed to pass through the aperture. So what is the meaning of this? Fresnel told that why will the diffraction occur? The diffraction occur because when the light is passing through this, now these portions of the light will not bend at all. These portions of the light will not bend at all, as you can watch in the figure. Okay, these portions of the light will not bend at all, but these portions of the light will bend. These portions of the light will bend. So due to the bending of these portions, the light is spreading. The light keeps on spreading. Due to the bending of these portions, the light will keep on spreading. Now this portion will not bend at all, but due to the bending of the light around the corners, the light will start to bend, and that is the cause of the diffraction. That will be the cause of the diffraction. Light here will not bend so much, but light here will bend, light here will bend, light here will bend. So due to the bending, it takes the form of a spherical shape. So this is the main cause of the diffraction. Clear? Next, diffraction of light at a single slit. So watch here. This is a slit AB. AB is a slit or an aperture. Okay. So we are taking a monochromatic source of light. So S is a monochromatic source of light. So light is coming out of the source, falls on a convex lens. It is kept at the focal length, and it gives parallel wave fronts. It gives parallel. So here light rays are coming out parallel. Here light rays are coming out parallel. The moment the light touches the aperture corner, the light will start to bend. So from here, please watch, if I keep a convex lens here, the light which is passing like this parallel, the light which is passing like this is again focused at the focal point, but the light which suffers diffraction, the light which suffers diffraction is focused here, the light which suffers diffraction will be focused here. Okay, so based on this, now let us see what is happening. So diffraction, as you can see here, diffraction occurs when light passes through the slit and is focused on the screen through the lens. The diffraction pattern, now here what happens? This is the portion of the light which is being focused here. The parallel rays gets focused here and the diffracted rays gets focused here. So what we will see alternate dark and bright bands with decreasing intensity. Please watch this thing. Decreasing intensity. Decreasing, that means as you move away, the intensity of the light will go on decreasing. As you can see, intensity of light will go on decreasing, and at the central part it will be the maximum intensity. Okay, the central part band or the central band, this is the central band, will be of the maximum intensity, is the maximum intensity, and as we move on both sides, the intensity of the light will go on decreasing. Clear? So let's see now. Okay, so okay friends, so here now we are studying position of secondary minima. That means I told you there will be alternate dark and bright bands, alternate dark and bright bands. Somewhere it will be dark, somewhere it will be bright. Okay, so this will continue. So we are now studying alternate dark and bright bands position. So first of all we are studying the minima. So minima will occur where, see, first of all please watch what is the path difference. The path difference here, this is the wave which is falling here. This much is the path difference of the wave. This much is the path difference of the wave. This is the path difference of the wave. Okay, so as you can see, the path difference is Bn, which is AB sine theta, which is A sine theta. A is the width of the slit. A is the width of the slit. So which is A sine theta. Now if the path difference is n lambda, that means if A sine theta is n lambda, we will have a minima. Please watch here. When the path difference is A sine theta, it will be minima. So the general formula for the minima condition is this. Please watch. This is the general formula for the minima condition. So sine theta equal to n by lambda, n lambda by a. Now where n equal to 1, 2, 3, 4, that means for the first minima we will put n equal to 1. For the second minima we will put n equal to 2. So this is n equal to 1 for the first minima. This is the minima, n equal to 1. So this is also n equal to 1. For the second minima, n equal to 2. N equal to 2 on both sides. For the third minima, as you can see here, n equal to 3. That means for the secondary, for the nth secondary minima, this is the formula for the minima condition, and putting n as 1, 2, 3, 4, we will keep getting at what positions we will be getting the minima. First minima will occur at what position? Okay, second minima will occur at what position? So we will get the positions of the minima, theta. We can calculate the sine theta. Second, we want to know the position for the secondary maxima. Where is the maxima? This is the maxima. Okay, this is the maxima. Then this is the maxima. This is the maxima. This is the maxima on both sides. So I want to know at what positions we will get the maxima. So the formula of the nth secondary maxima is this. When a sine theta, when the path difference will be this, a sine theta equal to 2n plus 1 lambda by 2, and when lambda n equal to 1, 2, 3, 4, we will get the secondary maxima conditions. So putting n equal to 1, we will get the first secondary maxima. For n equal to 2, we will get the second secondary maxima in this way. So the central bright maxima in the center we will get the brightest maxima. This is the center. We will get the brightest maxima along with secondary minima and maxima on other side. So see, so as I told you, this is the minima, this is the minima condition, this is the minima, and these are the maxima on both sides. Okay, and intensity will go on decreasing. So as you move on both sides, you will see that the peak of the graphs is going on decreasing. That means the intensity goes on decreasing. Next, let us see the next. The point O is the position of the central bright maxima and the points with path difference. So when path difference will be lambda, 2 lambda, 3 lambda, we will have the minima of decreasing intensity. Now we want to know what is the width of the central maxima. Okay, what is the width? So first of all, if I find the minima on either, so first minima will be a sine theta equal to 1 lambda, is first minima. Okay, so sine theta equal to lambda by a means theta equal to lambda by a, because theta is very small. Also as you can see that sine theta, as you can see here, sine theta, how can you find out? Sine theta will be we will take it as x by d. We will take it as x. This is our x by d, because since the theta is very small, so we will consider sine theta means tan theta. So we will take sine theta as x by d. That means x by d will be lambda by a. So x will be d lambda by a. So width of the central d lambda by a. So as you can see here, this is our x, this is our x, but the center, this is our x. This portion is the x, but the total width of the central maxima should be 2x. Okay, should be 2x. That means the total width of the central maxima should be 2x, which is 2d lambda by a, which is this. Now this D is actually the focal length of the lens. So in place of D, we can put F. In place of D, we can put F. So as the slit width increases, as you can see, that means increases, the maxima decreases. So width is actually inversely proportional to the width of the central maxima is inversely proportional to the slit width. That means as the slit width increases, the width of the central maxima will decrease. Now angular width of central maxima, angular width will be 2 lambda by A, 2 theta. So as you can see here, this is the angular width, this is the angle. So this is actually x by d, okay. So sine theta, the angular width, this theta is this theta. So we can tell this as width of the angular width of the central maxima, 2 theta. Now theta equal to lambda by A, theta is equal to lambda by A. So 2 theta equal to 2 lambda by A. This is the angular width of the central maxima. This is the angular width of the central maxima. Please note these formulas, very important. So 2d lambda by A and 2 lambda by A is the angular width of the central maxima. Next is difference in the diffraction pattern of a single slit due to a monochromatic and white light. Now if this is what we have shown with the help of a monochromatic light. Now if I would have used a white light, what would have happened? When the source is monochromatic, the diffraction pattern consists of alternate bright and dark bands. Please watch here. When you take monochromatic, when you take a monochromatic light, the diffraction pattern will be alternate bright and dark bands. Clear? And the central of unequal widths, these are important, of unequal widths, the central fringe has maximum intensity and intensity of successive secondary maxima falls off. Okay, so now when you are using a white light, the diffraction pattern is colored, the central maxima is white and other bands are colored. So we know that wavelength, we know that as the bandwidth is proportional to lambda, as you can see here, that our central maxima with 2x is proportional to the wavelength. That means the red band will have a higher wavelength, is wider than the violet band with a smaller wavelength. Okay, red has a higher wavelength. That means the central band with the red light will actually be more wider than the central band with the violet light because its wavelength is smaller. So with the white light, it will be the central band will be the white and other bands will be colored and overlapped, and the central band due to the red light will be the maximum width and central band due to the violet light will be the minimum width. This is what we will be observing. Next is the difference between interference and diffraction. So as we have already done interference, so due to it is due to superposition of two distinct waves coming from two coherent sources. Mind it, in interference we use two different coherent sources and we have two distinct waves, but in diffraction it is the superposition of secondary wavelets coming from different parts of the same wavefront. That means we are considering a single wavefront, not two waves. We are considering a same wave, and it is due to the superposition. all the bright fringes are of the same intensity, but here it will be are not of the same intensity. Intensity of minima is generally 0, and there is a contrast between bright and dark fringes. That means you can easily understand this is a dark band, this is a bright band, again this is a dark band, and this is a bright band, again this is a dark band, bright band, dark band, bright. So intensity you can easily differentiate, but here at minima it is never 0, and there is a poor contrast between bright and dark bands. That means you cannot, because intensity goes on decreasing, so you cannot distinguish after when you move out of the central band, okay, then the intensity goes on decreasing and you will never be able to distinguish which is a bright band, which is a dark band. But here this will continue. The width of interference fringes may or may not be equal. That means each width may or may not be equal, but here it is always unequal. Here it can be equal, cannot be equal, but here it is always unequal. Here it is always unequal. Next, let us study Fresnel's distance. So what is Fresnel's distance? It is the minimum distance a beam can travel before its deviation from straight line path becomes noticeable. That means how much it can travel, this basically this much, how much it can travel before it gets deviated, how much it can travel straight, okay, so how much it can travel straight before it gets deviated, how much it can travel before it gets, so this is the Fresnel's distance. How much will it travel before it starts to get deviated? That is the Fresnel's distance, okay, ZF. It is given by a square by lambda. A is the width of the slit. Next is the resolving power of an optical instrument. What is it? Resolving power of an optical instrument. It is the ability of the instrument to produce distinctly two separate images of two close objects. Okay, when you are seeing two close objects, resolving power means how easily these can be seen as two different objects. How easily it can be seen as two different objects is called the resolving power of the optical instrument. The minimum distance between two objects which can be just seen as separate by the optical instrument is called limit of resolution. So this is the limit of resolution. Smaller the limit of resolution of the optical instrument, greater is the resolving power. If this is smaller, if the objects are very close, so smaller is the limit of resolution, greater is the ability to see them as separate objects. Next, resolving power of a microscope. So please watch here. Resolving power, D is the distance between the two point objects and mu is the medium between the object and the lens. That means this is the object, D is the distance between two objects, this is the D, and here is the mu, is the refractive index of the medium between the object and the lens. So this is given as the resolving power of the microscope. Thus, to increase the resolving power, we decrease lambda. So this is the resolving power. This is the resolving power. So resolving power, as you can see, is inversely proportional to the wavelength of the light used. Similarly, resolving power of a telescope, this was microscope, 2 mu sin theta by lambda. Again, these are the two different objects. D is the diameter of the objective lens of the telescope. This is the objective lens. D is the diameter. So diameter, so radius will be D by 2. So focal length of the lens will be r by 2, which is d by 4. This is the focal length of the lens used. This is the lens used, focal length of this much. So resolving power is given as d by 1.22 lambda. This is the resolving power of the telescope. So to increase the resolving power of the telescope, the objective lens should be of a larger diameter. That means you have to take a bigger lens whose diameter will be much more. Then only you can resolve the objects very clearly. So for microscope it is 2 mu sin theta by lambda, and for the telescope it is d by 1.22 lambda. Now Doppler's effect in light. Whenever there is a relative motion between a source of light and observer, the apparent frequency of light received by the observer is different from the true frequency of light emitted from the source. For example, you are observer here, and here is a source which is emitting light, of frequency this. So when you are moving and source is also moving towards each other or away from each other, definitely you will not see the same frequency of light. There will be a change in the frequency of light. So that is Doppler's effect. If the object and the source move close to each other or away from each other, the light emitted by the source will not be seen as the frequency this. There will be a change in the frequency. You will see there is a change in the frequency of the light. So this is the formula. This is your observed frequency. This is the actual frequency. This is the velocity of this is the v is the, as you can see, relative velocity between the observer and the source. Okay, and c is the velocity of the light used. C is the velocity of the light used. This is the frequency of the light emitted. This is the frequency of the light observed, and v is the velocity, relative velocity between the observer and the source. V is the relative velocity between the observer and the source. C is the velocity of light. So please watch here. When the source and observer are approaching each other, we take the plus sign here, and when they are away from each other, receding away, we take the minus sign here. Please watch here. When the source and observer are moving close to each other, we take the plus sign, and when they move away from each other, we take the minus sign. So keeping this, so this is the velocity of the relative velocity between the source and observer. This is the change of the frequency observed when the source and observer are moving. This is the velocity frequency of light emitted by the source. Okay, so in terms of wavelength we can write like this. So plus will be taken when the source and observer are moving towards each other, and minus will be taken when source and observer are moving away from each other. So this is the change in the frequency as observed, actual frequency. This is the change in the wavelength as observed. This is the actual wavelength of the light emitted. This is the speed of light, and this is the velocity of the relative velocity of the source and the observer. Next comes blue shift and red shift. What is blue shift? When the source and observer approach each other, so we know that this will be taken as positive. The change in the frequency is taken as positive. The apparent frequency increases or apparent wavelength decreases. Okay, so apparent frequency will increase, and we know V equal to F lambda. V equal to F lambda. We know that V equal to F or nu lambda. So what is nu? Nu is inversely proportional to the wavelength. That means if the apparent frequency increases, the apparent wavelength will decrease, and when you are decreasing the wavelength, you are moving towards the smaller wavelength. So we call it a blue shift. We call it a blue shift. Similarly, when the source and observer recede away, then apparent frequency decreases, and when apparent frequency decreases, the apparent wavelength increases. So wavelength increases means you are moving to the higher wavelength. So it is called the red shift. It is called the red shift. So this is the blue shift and this is the red shift. So we call it blue shift. Apparent frequency will increase and apparent wavelength will decrease. Similarly, in the red shift, during the red shift, we will call it the apparent frequency decreases and apparent wavelength increases. Okay, this is called the red shift. So now let's move on to the next one. Applications of Doppler's effect. So where can we use it? Measuring the speed of a star and galaxy, measuring the speed of rotation of sun, estimation of speed of aeroplanes, rockets and submarines, and estimation of velocity of satellites. Clear? These are the fields where we use the Doppler's effect. Next, a very important topic called the polarization of light. Polarization of light. So let's see what it is. Light is an electromagnetic wave in which electric and magnetic fields are vectors are sinusoidally perpendicular to each other. That means if, please watch here, y-axis, z-axis, x-axis. So electric fields and magnetic fields will be like this. Okay, so electric field is like this, magnetic field is like this. They are perpendicular to each other and also perpendicular to the wave direction. So that is the electromagnetic wave. That means in which electric field, magnetic field will be perpendicular to each other as well as perpendicular to the direction of propagation of the light. That means if the light is proceeding like this, the electric field is like this, the magnetic field will be like this. All will be perpendicular to each other. All will be perpendicular to each other. So that is why it is called an electromagnetic wave. The light from a bulb is unpolarized. When unpolarized, so when the unpolarized light is passed through a tourmaline crystalline. So this is, see, this is the tourmaline crystalline. This is the unpolarized. That means this is the electric vector and dot is the magnetic vector. Please make sure here the dot is actually the magnetic field. Okay, this is the electric field. So electric field is shown like this and magnetic field is actually into the paper. So we show it with the help of a dot. They are perpendicular to each other and this is the direction of the wave going on. So it is an unpolarized. That means both electric and magnetic fields are there. So this light is coming from a bulb and when it is allowed to pass through a tourmaline crystalline, only those vibrations of light pass through the crystal which are parallel to the AB. So see, this is the cutting of the tourmaline. That means only electric fields will be allowed to pass but not magnetic fields. So see, the dots are not there. The circular dots are missing. That means only electric field vectors will be allowed to pass through. All other vibrations are absorbed. The intensity of light coming out is reduced because yes, one component, that is the magnetic field, is being absorbed. The emergent light, which contains vibrations only in one direction, is called plane polarized light. So see, this is how happened. This is the unpolarized light This is the unpolarized light passing through a tourmaline. You see the lines which are cutting here are parallel lines, as you can see. They are parallelly cut like this. So electric field vectors are allowed, magnetic field is absorbed. Okay. Again there is a parallel cutting. So the second tourmaline will be called as an analyzer. First one is called a polarizer. So again see, only the electric vectors are coming out. Clear? But if now here if I do parallel cutting, that means from the polarizer the electric field vectors will come out. But here they are cut like this. That means the electric field vectors are also stopped. So no light will come out. So analyzer will send no light. That means here intensity will be 0. Okay. Here although intensity will decrease, but here if it is cut perpendicular to the electric field, that means the analyzer will allow no light to pass through. Next, detection of polarized light. So how would you detect a polarized light? A quartz crystal, a Nicol prism, a quartz crystal or a Nicol prism can be used as a polarizer as well as an analyzer of polarized light. So this is what I am telling, is that this you can use as a quartz prism or a Nicol prism. Both polarizer and analyzer we can use made of this. Now, when unpolarized, so when unpolarized light, unpolarized means both the electric and magnetic vectors are there. So when unpolarized light is seen through a single crystal, intensity of the transmitted light will decrease because one of the components will be absorbed. On rotating the crystal, intensity of polarized light does not change. Okay. However, when the light transmitted from the polaroid P1 is seen through another polaroid P2, the intensity falls from maximum to 0. Between P1 and P2 varies from 0 to 90 degree. Now watch here what I am telling, that is, please watch the things here. When only the polarizer is turned, that means the intensity will not change. Intensity of light here will not change. And when the analyzer is turned through 0 degree, from 0 degree to 90 degree, slowly, the intensity coming out here will be from 0 to maxima, and again from maxima to 0. This is how it will vary. On turning the polarizer through an angle, there will be no change in the intensity. But when the analyzer is turned, through 0 to 90 degree, we will see that intensity falls from 0 to maxima and then again to 0. Okay. Now, next part is the Malus law, law of Malus. What is Malus law? When a beam of completely plane polarized light is incident on an analyzer, that means from the polarizer we come to the analyzer, the resultant intensity of light transmitted from the analyzer. So how much light will come out? Suppose light here is I, intensity is I. So after it comes out from the analyzer, is that intensity is directly proportional to the square of the cos of the angle between the analyzer and the polarizer. Square of the, suppose the polarizer is like this and the analyzer is like this. Okay, so what is the angle between the polarizer and the analyzer? It is theta. So the intensity of the light which will come out will be proportional to the square of the angle between the polarizer and the analyzer. Okay, so this is the Malus law. So to remove the proportional, we take a constant Ka square. A is the amplitude of the plane polarized light. Amplitude of the plane polarized light. Okay, and that is I0, intensity of the original light. So if theta is 90 degree, that means if the angle between polarizer and analyzer is 90 degree, the intensity of the light coming out will be 0. And when the theta is 0 degree or 180 degree, the intensity of light will remain same. The intensity of light coming out from the analyzer will remain same. Here the light coming out from the analyzer will remain same if it is 0 or 180. And if it is 90 degree, the light coming out will be 0. To prove that when unpolarized light is passed through a polarizer, its intensity becomes I0 by 2. They are telling that when a light is passing, when the light will pass through the polarizer, unpolarized light, when it is passed through the polarizer, show that intensity becomes I0 by 2. So let us take this. First of all, please try to understand this concept, which is very important. Very important. Average of cos square theta over a cycle of 0 to pi. Average of cos square theta over a cycle of 0 to pi is written like this. Okay, so now we will take half and this becomes 2 cos square theta. We make it 1 by 4 pi, and we will write here, we will make it 1 by 4 pi. So this will become 1 by 4 pi, and this will become 2 cos square theta. Okay, so here, and 2 cos square theta is 1 plus cos 2 theta. So it is theta, it is only d theta plus cos 2 theta. So integrating it, we get theta, and this is sine 2 theta by 2, which is 1 by 8 pi. Putting the value of 2 pi and 0, and then 2 pi and 4 pi and 0. This is, so it becomes half, and this becomes 0. That means average of cos square theta is coming half. That is why we can tell that the intensity of the light coming out, unpolarized light coming out of the polarizer, will be I0 by 2. Intensity of light coming out from the polarizer will be I0 by 2. Next, Brewster's angle. So what is Brewster's angle? So watch here. The angle of incidence at which the reflected light is completely plane polarized is called polarizing angle or Brewster. So see, this is the unpolarized light, both electric field and magnetic fields. This is magnetic field, this is electric field. Both are falling on a substance of density refractive index mu. Here one component gets polarized, magnetic field comes out here, and this is the component, the rest component passes through here. This is polarized, this is unpolarized. They should be at the angle at which the reflected light is completely plane polarized. So see, this is the plane polarized, that means you have only magnetic field here. So that angle, this angle is called the Brewster's angle. This angle is called the Brewster's angle. Okay, unpolarized light reflected back as plane polarized light. So that angle will be called as the Brewster's angle. Next is Brewster's law. What is Brewster's law? When unpolarized light is incident at polarizing angle IP on an interface separating air refractive index mu, then reflected light is fully polarized. This is, see, fully polarized. The reflected light is fully polarized, and we can write the relation mu equal to tan IP. This is BREWSTERS law. This is the BREWSTERS law. Mu equal to relation between the refractive index and the angle of polarizing angle is mu equal to tan IP. So let us see the proof of BREWSTERS law. Okay. So as you can see that this angle will be perpendicular. This angle will always be perpendicular. In reflection, this angle is equal to this angle, and this angle, this is the refracted angle. This angle is always perpendicular. So I can write 90 minus IP. And YOC I can write 90 minus R equal to 90. So I equal to IP according to Snell's law. So here, please watch here. Snell's law tells sin I by sin R equal to mu. So here I is actually the polarizing angle. So sin IP by sin R is mu. So sin IP equal to mu into sin R. R can be written as 90 minus IP cos IP. So tan IP equal to mu. So this is the proof of the BREWSTERS law. In case of reflection at BREWSTERS angle, the reflected and refracted rays are always mutually perpendicular. That means if it is the BREWSTERS angle, then the reflected and the refracted rays should always be perpendicular to each other. So let's see. Mu equal to tan IP, sin IP by cos IP. Snell's law says this. So instead of, that means sin R equal to cos IP. Okay. So sin R equal to sin 90 minus IP. Sin R equal to cos IP, as we know that. Please watch here. Mu means sin IP by cos IP, and mu also means sin IP by sin R. So I can tell sin R means cos IP. Here sin R means cos IP. So cos IP is 90 minus IP. So IP plus R is equal to 90 degree. This is the relation. Next, uses of Polaroid. The Polaroid, what are Polaroids? So Polaroids are materials which polarize light, like tourmaline. Tourmaline is a natural Polaroid. And where do we use the Polaroids? To avoid glare of light. That means in our sunglasses we use it. To get clear photographs of white clouds. Fitted in the windshields of cars during night driving. The objective lens of the microscopes to observe minute particles and three-dimensional motion pictures. We use the Polaroids in these cases. Now friends, let's see the numericals of this chapter. First numerical is, we are using a red light of wavelength this is the slit width A. Find the distance between the first two dark bands on each side. Now dark bands, as we know that first two dark bands, that means the central band, and central band distance is 2x, which is 2 lambda d by A. The width of the central maxima is 2 lambda d by A. Using this 2 lambda, d is given, A is given, we get the width of the central maxima. Find the angular spread between the central maxima and the first order maxima due to a slit width. This is the slit width A. wavelength given incident normally. That means they are telling that find the angular width between the central maxima and the first order maxima. Okay, central maxima and the first order maxima. What is the width? So a sine theta is equal to 2n plus 1. This is the central, this is the maxima condition. 2n plus 1 lambda by 2. Instead of theta, we are taking theta. Angular width we want to find. So first order maxima means n equal to 1. Lambda I know, a I know. So we get this answer. This much radian is the angular spread between the first order maxima and the central maxima. Now lambda given to us, width of the aperture given to us, what distance traveled by the diffracted ray does the spreading due to the diffraction becomes greater than the width of the aperture. That means diffraction will now start. So using Fresnel's law, this is the Fresnel's distance, a I know, lambda I know, we can get. That means minimum how much it can travel before it gets diffracted. Next, light reflected from the surface of a glass, refractive index given is plane polarized. Find the angle of refraction. So we know this formula, mu equal to tan IP, mu I know. So we can find out IP, which is coming this. Now we know IP plus R equal to 90 degree. So R will be this. So this is the angle of refraction. Light of wavelength lambda given is incident on an aperture A given, lambda given, A given. Find the distance up to which the light ray can travel such that its spread is less than the size of the aperture. That means again, minimum distance how much it should travel before it gets deviated. So Fresnel's distance I have to find. Next is light of wavelength is incident normally on a slit of width this. Find the linear width of the central maxima on a screen kept D. So D given. That means 2x they are asking, which is 2d lambda by A. So here we get it. A slit of 4 centimeter wide A given, wavelength given, find the angular spread of the central maxima. So angular spread, as you can know, that is the 2 theta equal to 2 lambda by A. So putting the form values, we get the answer. A screen is placed 2 meter away, that means D given, narrow slit, find the slit width, A I don't know. If the first minima lies 5 millimeter on either side of the central maxima, okay, x given, x is given to us. So sine theta equal to first minima means n equal to 1. This is the minima condition. So sine theta equal to lambda, and sine theta is also x by d. So x by d. So A is lambda d by x. So putting the value of lambda d, we get the answer. Two spectral lines of sodium have wavelengths this and this. So there are two wavelengths. A sodium lamp sends incident waves on a slit of width. This is A given to us, A. D given, screen is 2 meter away. Find the spacing between the first maxima. First maxima means central width. It is the central width, okay. So this is the maxima condition. Sine theta equal to this. Sine theta is also x by d. That means I have to find x, and then, so this is the x. So from here we know that if n equal to 1, because they are telling find the spacing between the first maxima So n equal to 1. Putting n as 1 here, we get, and then putting n as between the first maxima, spacing between the first maxima. Okay, using both the wavelength, using this wavelength, we will get, this is the distance of the first maxima, and this, using this wavelength, we will get the distance of the first maxima. Now we have to find the difference between the two distances. So putting the values and calculating, we get this. That means using this light, we will get the first maxima at this much distance from the center. Using this light, we will get the first maxima at this much distance from the center. So now they are asking what is the difference between the two distances. A screen is placed 50 centimeter away, D I know, wavelength I know, and the distance between the first and third minima. So this is the minima condition. First minima n equal to 1. Okay. This is sine theta. This is sine theta equal to n lambda by a. So x is this. Now first minima n equal to 1. Second minima n equal to 2. Between the first and the third. So third minima is this. Now we find the difference between this. So putting the values, we get the answer. Single slit, first minima for red light. So wavelength I know coincides with the first maxima of some other wavelength. So first minima, using the minima condition, okay, sine theta equal to n lambda, a sine theta equal to n lambda. So sine theta equal to n lambda by a. So here n will be taken as 1. Okay, so the condition here is, this is the condition for the maxima. First maxima will be, sine theta will be 2n plus 1 lambda by 2. Okay, and sine theta will be what? We know sine theta, please watch here, sine theta will be what? A sine theta equal to n lambda. So sine theta will be what? N lambda by a, and sine theta is x by d, n lambda by a. So here x will be n lambda d by a. Okay. Now for the first maxima and for the first minima, this is the minima condition. So n equal to 1, we will take n lambda by a. And for the first maxima condition, we will take 2n plus 1 lambda. Okay, so please watch here. X equal to, here we will take n equal to 1 because the first minima, lambda d by a. Okay, now they are telling for the first maxima, it will be what? X by d will be equal to this. By a. So x will be what? 2n plus 1 lambda by 2 a into d. Now here n equal to 1, that means x will be 3 lambda d by 2a. Now they are telling that these two, for this lambda, this is the distance of the first minima. For this lambda, this is the distance of the first maxima. They are telling these distances are same. So equating that, we get what? Lambda d by a should be lambda dash. This is with lambda dash. 3 lambda dash d by 2a, a cuts, d cuts. Okay, so lambda dash will be how much? It will be 2 lambda by 3. 2 lambda by 3. If I do 2 lambda by 3, then we will be getting that, a lambda. Next is wavelength of the light used is this much on a slit with a given, lambda given. Find the angular width. Angular width, we know that it is how much? Angular width theta will be lambda, n lambda by a, n lambda by a, angular width. And linear width x, so it is 2 theta, total theta equal to this, so total angular width is actually 2 theta, which is this. And linear width will be x by d, so we need 2x, that is the linear width. So putting the values, we get this is the linear width. Now we see they are telling that if d is doubled, the angular, now d with angular width, there is nothing with d, so angular width will not change if I double the distance of the screen and the aperture. Next question is, a telescope has an objective of diameter 60 centimeter. Okay, so this is with the resolving power. The focal length of the objective and the eyepiece are 2 meter and 1 centimeter. So diameter is 60 centimeter, which is this. Objective focal length and eyepiece focal length is given to us. Distance between the stars is 10 to the power 4 light years. 1 light year is this much, 9.46 10 to the power 15 meter, which is this. Now, separation between the two stars are given to us. The two stars separation is given to us. They are telling what is the angle subtended by the transverse separation of stars. That means this separation will subtend what angle. So it is very clear, it is the 10 to the power 10 by the distance. That is actually acting as perpendicular by base. It is actually acting as perpendicular by base because it is so far away that we can consider this as perpendicular by base and we can calculate the angle. Limit of resolution of the telescope is given 1.22 lambda by d. Okay, so 1.22 lambda diameter of the thing is given to us. So this is the limit of resolution of the telescope. Since the angle subtended by the transverse separation is much less than the limit of resolution, so the stars cannot be resolved. So watch here, this angle is angle subtended by the stars on the telescope is this, and limit of resolution is this. That means I can see that the angle subtended is very, very less compared to the limit of resolution. So we cannot see the stars. We cannot actually see the stars. Angle subtended on the telescope is only this much. Okay, and the limit of resolution is this much. So this angle is very less than this, so we cannot see the stars. Next, find the resolving power of the microscope with angle of light falling 60 degree and wavelength given to us. Refract. So resolving power of the telescope of the microscope is 2 mu lambda by this. So 2 mu sine theta by this, we get this. Now wavelength is using this from a star, which is what is the limit of resolution of the telescope. Objective diameter is given 100 inch. So limit of resolution of the telescope is 1.22 lambda by d. Now 100 inch means 2.54 into 10 to the power minus 2 centimeter meter. So this is the limit of resolution. Next is the diameter of the pupil of the human eye. This is the diameter. And wavelength given to us, find the limit of resolution, which is 1.22 lambda by d. Next, the spectral line for a given element in the light received from a different star is shifted towards the longer wavelength by 32.032%. Deduce the velocity of the star. So please watch one thing. Towards the longer wavelength, that means you are moving towards the longer wavelength of this. So if the wavelength is increased, that means the frequency will, if the wavelength of the light is shifting towards longer wavelength, that means this is taken as positive. So the star is moving away. So V is taken as negative using the formula this. So this is C, value of the C, and this is the percentage. Okay, this much percentage is the wavelength increased. So we can see that the star is moving away from us. The frequency is decreasing. It is moving towards a greater wavelength, means frequency is decreasing. That means it is moving away. So this is the speed of the star moving away. With what speed should a galaxy star move with respect to the sodium light? Wavelength given and is observed at this. So what is the change in the wavelength? Wavelength is increasing here, so star is moving away from us. So this is the change in the wavelength by original wavelength minus V by C. So this is the velocity with which the star is moving away from us. Next, at what angle of incidence IP is reflected from the water refractive index completely plane polarized? That means we will use mu equal to tan IP. IP will be this. So this is the angle of the polarization. This angle depends on the wavelength of light. Definitely this angle, because mu is depending on IP. IP is depending on mu, and mu depends, refractive index is inversely proportional to the wavelength. So IP will also depend on the wavelength. Two Nicols are oriented so that maximum amount of light is transmitted. Okay. To what fraction of its maximum value is the intensity of light transmitted reduced when the analyzer is rotated from through 30 degree? Okay. So please watch. We know this intensity of light coming out from the polarizer is this. So I by I0 is cos square 30. So this, that means it becomes 3/4. That means 25% is, okay. So this is 25% gets reduced. That means 75% gets transmitted. Now when it is 60 degree, so it becomes 1/4. That means 25. It becomes only 25%. That means 25% is transmitted. 75% gets reduced. Next, the refractive index is given. What is the angle of refraction? So here the angle of refraction we can find, and then they are telling what is if the angle of, if the unpolarized light is incident on it at the polarizing angle. So polarizing angle, that means they are asking what is the angle of refraction. We know IP plus R equal to 90. We can find R. An unpolarized light beam is incident on 4 polarizing sheets which are arranged in such a way that the direction of each polarizing sheet makes 30 degree with that of the preceding sheet. What is the fraction of the light transmitted? Okay, so after the first sheet, it will be I0 by 2, right? After the second sheet, it will be I0 by 2 cos square 30, which is this. We know that after the first polarizer, it becomes I0 by 2. Now this angle, if it is changed by 30 degree, so how much will it be? This. And then if it is changed by again 30 degree, so this is coming here, this into cos square 30 is this. Again it is changed by 30 degree, so this into cos square 30 is this. That means this was the original and this is the final. So this is the fraction of the light which is getting transmitted. Next, unpolarized light is incident on a plane surface. What is the angle of incidence? So that reflected and refracted rays are perpendicular. So reflected and refracted rays are perpendicular when it is at the polarizing angle. Clear? For a given medium, the polarizing angle IP is given to us. So when we know that mu equal to tan IP, so tan 60, mu I know, and mu equal to 1 by sin C. C is the critical angle. So we can find out the critical angle. They are asking what is the critical angle. Now the critical angle of a transparent medium, critical angle is given to us. We know mu equal to sin 1 by sin C and mu equal to tan P. So tan P is equal to 1 by sin C. So P equal to tan inverse cosec C. And we know that polarizing angle and reflected angle are at 90 degrees. So R will be this. So 90 minus the polarizing angle. Okay. So 90 minus R is equal to this. So tan 90 minus R is cosec C. So cot R equal to cosec C. This is the relation between the refracted and the critical angle. Next, two Polaroids are at 90 degree to each other and transmitted intensity will be 0. Okay, so this is the relation of the intensity coming out. After the first, we know it is always I0 by 2. Okay. After the second, because here they are telling that two Polaroids are 90 degree to each other. What happens when one more Polaroid is placed between these two, bisecting them? That means this is one polarizer, this was the other polarizer, the angle was 90 degree between them. One more Polaroid is bisecting both of them. That means the angle has to be 45 degree. So using this, so intensity of the light is reduced by 1/4, so 3/4 is transferred. The direction of light will be same as the coming from the first Polaroid. So direction will not change. This direction will always remain the same. So friends, with this we finish the diffraction and polarization of light chapter, and I hope you have understood, but please go through the numericals. Before that, you should always go through the theory very clearly and watch the things. Okay, first of all practice the theory lot and then only you will do the numericals. So I hope you have understood, and if you have understood, please keep following Parijat sir classes. Okay, so till then, it's thank you and goodbye from my side.